Hi, this lesson is about the average value of a function, and later on we'll talk about the mean value theorem for integrals. So remember what you know about the average value of a finite number of numbers. Suppose we have n numbers from 1 to n. So in order to compute their average, you would be adding all of the numbers from 1 to n and dividing by the number of numbers, which is n. Remember that top expression is summation notation, which means that you add all of your numbers starting with the lower index value of 1 and ending with the upper index value of n. So that's our average for a finite number of numbers. So if we wanted to find the average value of a function, that means we're trying to find the average value of the y values or the f of x values. But if you're considering a continuous function on a closed interval, even though it's on a closed interval, you have infinitely many function values on that closed interval. So it's not quite as straightforward as just adding some numbers and dividing by the number of numbers. But we can use what we know in order to come up with a definition. So if I wanted to compute the average value of a function, this is our notation, f sub AVE for average. This is your typical average calculation that we just talked about, but we're going to let our limit, take our limit as n approaches infinity, meaning that the number of numbers approaches infinity, which is exactly what's going on for a continuous function on a closed interval. There's infinitely many function values. Okay, but in order to get a better definition, we're going to use information that we've used in the past. Remember, when we talked about Riemann sums, we said that delta x is computed by subtracting b minus a divided by n. And if I take that definition and solve for n by cross-multiplying, you get n equals b minus a over delta x. But remember, as n approaches infinity, your delta x is actually your differential dx. So we're going to put this all together in order to get the definition for the average value of a function. So if the average value of my function is the limit as n approaches infinity of your sum of all of your functions divided by n, suppose I let n equal what we just computed and put that in here. So now I have the limit as n approaches infinity of the sum as I goes from 1 to n of f of x divided by what n is equal to, which is b minus a over delta x. Okay, so that means we're dividing by a fraction, and dividing by a fraction is the same as multiplying by the reciprocal. So when you do that, you get the result here on the right. I have the limit as n approaches infinity of the sum of f of x sub I times delta x over b minus a. But the numerator is my Riemann sum. And remember, my Riemann sum is the definite integral. So if I replace this definition with the definite integral, you get that your average value is what you see here in this pink box. It's 1 over b minus a times the integral from a to b of f of x dx. And so that's a definition that you would want to memorize. All right, so let's use this definition in order to compute the average value of a function. So we want to find the average value of f of x equal to 1 plus x squared on the closed interval from -1 to 2. All right, so you're basically just plugging into the formula that we just discussed. So I have the average value is 1 over 2 minus -1 times the integral from -1 to 2 of 1 plus x squared dx. So this is a very straightforward integral. You just have to take the antiderivative of a constant, that gives you x, anti-power rule, that gives you 1/3 x cubed. And then you just have to evaluate that definite integral by using the fundamental theorem of calculus. So you plug in the upper limit first, which is 2, and then subtract when you input the lower limit. So make sure you change your sign. So that's why you have a minus here and a minus right here. Okay, so when you do the arithmetic on that, you get 1/3 times 6, which gives me an average value of 2. which means the average function value, the average y values for this function on that closed interval is an average value of 2. All right, so now let's talk about the mean value theorem for integrals. Mean value theorem for integrals is not the same as the mean value theorem that we learned when we learned our derivatives, but it is related to the average value definition. So the theorem says if f of x is continuous on a closed interval, then there exists a number c within that interval, and it could equal a or b. So it's c is in somewhere in the closed interval from a to b, such that f of c is equal to the average value. So in other words, the function at c has the same value as the average value on the closed interval. And you can set up an equation that looks like this, that your integral, which remember represents the area under the curve of f of x, is equal to f of c times b minus a, which is an area in and of itself. So we'll look at that with an actual example in next problem. All right, so we want to find the value c that satisfies the mean value theorem for integrals for f of x equal to 1 plus x squared on the closed interval from -1 to 2. So this is the same function we used before when we had average value. So a lot of the same work will be the same. So we're going to look at this from a different perspective. So remember, the definition says that f of c equals the average value. So that's the equation that I set up here. The average value calculation is the same calculation we did above. So that has a value of 2, which we did earlier. Remember, that's equal to f of c. So I'm just going to substitute c into the original function. So then I get 2 equals 1 plus c squared. Solve for c, and you get that c is equal to plus or minus -1. Plus and minus -1 falls within the interval, so both of them are solutions to what we're looking for. And notice that your function value at plus or minus -1 equals 2, which is the same thing that your average value equaled when we did the computation, which is the whole point of this. Okay, so now let's look at this from a graphical perspective. So on the left side, I drew the graph of 1 plus x squared from -1 to 2, and I shaded the area underneath that curve with respect to the x-axis. The value of that integral, or the area, is 6. Similarly, I took the right side of the definition for the mean value theorem for integrals, which is that f of c times b minus a. And that's also equal to an area. Remember, for us, our f of -1 or 1 has a value of 2, which is why you have 2 up here. And if you took that space and computed the area, well, that's just a rectangle. So it has a height of 2 and a width of 3. So that has an area of 6. So these two should be equal if it satisfies the mean value theorem for integrals. Okay, so let's get back and use both concepts we just talked about. Let's do another average value problem. Find the average value of f of x equal to the cube root of x on the interval from 1 to 8. All right, so again, this is just asking for average value. So I'm using the first definition I gave you. This is 1 over 8 minus 1 times the integral from 1 to 8 of x to the 1/3 dx. Again, this is a straightforward integral. You just have to do anti-parallel. So you have the next line. So it's 1/7 times 3/4 x to the 4/3. Substitute in your upper limit and your lower limit and make sure you subtract them. And when you work that out, you get an average value of 45 over 28 on that function. Okay, here's another one. We want to find the average value of f of t equal to t e to the -t squared on the closed interval from 0 to 5. Okay, again, this is just straightforward using the definition. Average value is 1 over 5 minus 0 times the integral from 0 to 5 of t e to the negative t squared dt. All right, so this integrand isn't quite as straightforward as the previous ones. Here you have to use substitution. This is a product, and one of your factors is a composite function, which is e to the negative t squared. So we let u equal the inner function, which is negative t squared. So the substitution is found right here, substitution information. So u is negative t squared, d is negative 2t dt, but you have t dt in your original problem. So get rid of the negative 2 by multiplying by negative a half. So negative 1/2 du equals t dt, and that's what gets substituted for what I underlined in the original problem. I'm also going to reevaluate the limits. So when my lower limit is 0, when t is 0, you plug into u right here. U is also 0. When t, the upper limit, is 5, your u is negative 25. So now I can actually do my substitution, which is what you see here. The outside part stays the same with the 1 over b minus a still stays the same. That's outside of the integral. And then I can rewrite my integral as follows. So I have the integral from 0 to negative 25, negative 1/2 e to the u du. So that's now a much simpler integral to handle. The antiderivative of e to the u is itself, and I also multiplied the 1/5 and the negative 1/2 to get negative 1/10 e to the u evaluated from 0 to negative 25. Substitute the upper limit first, so this is e negative 1/10 times e to the negative 25 minus e to the 0. And e to the 0 is 1, and e to the negative 25 is 1 over e to the 25. So I just flipped the order, and the sign of the outside negative 1/10 becomes positive 1/10, and so that's your average value. All right, here's another average value problem where, again, you'll have to use some substitution. So we want to find the average value of h of theta equal to cosine to the 4th of theta, sine of theta on the interval from 0 to pi. This is, again, a product, and one of them is a composite function. The cosine to the 4th of theta is a composite. So here's your average value definition. It's 1 over pi minus 0 times the integral from 0 to pi of your integrand. So here's the u substitution work. We're going to let u equal the inner function, cosine of theta, du, or the derivative of cosine, is du negative sine of theta d theta. Make sure you leave your differentials on different sides of the equation here. So you have sine theta d theta, not negative sine theta d theta. So multiply by negative 1, and negative du replaces or substitutes what I underlined in the original problem. Then again, I reevaluate the limits. When your lower limit, theta, is 0, your upper limit, u, is cosine of 0, which is 1. When theta is pi, u is cosine of pi, which is negative 1. So 1 and negative 1 are your new limits. All right, so we plug in that information here. So I have 1 over pi, the integral from 1 to negative 1 of negative u to the 4th du. So remember, with u substitution, you should, after you do your substitution, you should have a simpler integral to evaluate. If it's more complex, you probably did something wrong with your u substitution. So here we take the antiderivative. So I get 1/5 u to the 5th, and I pulled out the negative along with the 1 over pi. Substitute in your upper limit and your lower limit. Remember, your upper limit is the smaller number, negative 1, and your lower limit is the larger number, 1. And that's because of the relationship that we established above. So now you do the work. The inside of the bracket becomes negative 2. Multiply negative 2 by negative 1 over 5 pi, and you get 2 over 5 pi is your average value. Okay, so here's another, more of a word problem, but it's regarding average value. So in a city, the temperature in degrees Fahrenheit, T hours after 9 a.m. was modeled to be the function T of T equal to 50 plus 40 sine of pi T over 12. And we want to find the average temperature during the time period from 9 a.m. to 9 p.m. So in order to set up our average value definition, you're going to have to relate these times, 9 a.m. and 9 p.m., in terms of t. So you wouldn't want to use 9 and 9 as your limits. That wouldn't make sense. So we're going to let 9 a.m., the initial time, be time t equals 0, and 9 p.m., 12 hours later, be time t equal to 12. So those will be the limits for your average value. So if we apply that to our average value definition, I have 1 over 12 minus 0 times the integral from 0 to 12 of 50 plus 14 sine of pi t over 12 dt. All right, so now we're ready to take the antiderivative. The antiderivative of 50 is straightforward. That's just 50t. Here, for 14 sine of pi t over 12, I actually used u substitution. I didn't write it out, but I'll do it here for you. Because sine of pi t over 12 is a composite function, so the inner function is, oops, I wrote this wrong. So the inner function is pi t over 12. So du is pi over 12 dt. And if I solve for dt, which is what you have here, you get 12 over pi du equals dt. Okay, so I kind of took a shortcut with that because it was just really just this factor that I have to worry about. So that's what you see here. My antiderivative is 14 times 12 over pi times the sine of, times the cosine, because cosine is the antiderivative of sine, of pi t over 12. So I left everything in terms of time, so I don't have to reevaluate my limits. All right, so now I have to evaluate this from 0 to 12. Plug in 12, and then subtract out, plugging in 0. And so be careful with the 0. A lot of times when we plug in 0, everything just cancels out, but it doesn't this time because cosine of 0 is 1. So I've written it all out for you. So inside the parentheses, you get 600 plus 168 over 12 plus 168 over 12, which gives you 600 plus 336 over 12. And if you, I'm sorry, not over 12, over pi. And if you distribute 12 across this, 12 goes into 600 and 336. So your average value, the exact answer is 50 plus 28 over pi. And if you approximate that, that's about 58.9 degrees Fahrenheit. All right. So let's put this all together. Let's find the average value and use the mean value theorem for integrals. So you're given that f of x equals x minus 3 squared defined on a closed interval from 2 to 5, and you want to find the average value. All right, so again, pretty straightforward. Average value is 1 over 5 minus 2 times the integral from 2 to 5. This is also a composite function, but it's a pretty simple one, so you don't really have to use u substitution, because notice that the derivative of my inner function is just 1. If it had been something even just slightly more complicated, like 2x minus 3, you would want to use u substitution to help you think that through. But here you're really just doing anti-parallel. So when I take the antiderivative, it'll be 1/3 times a third times x minus 3 to the third power. All right, so the 1/3 and the 1/3 becomes 1/9, and then we plug in our upper limit and subtract out, plugging in our lower limit. So you get 8 minus -1, or 9 on the inside, and 1/9 times 9 gives me an average value of 1. Okay, so that's done. Now let's go to part B of the same problem. We want to compute the value c such that the average value equals f of c. So that's your mean value theorem for integrals. All right, so the average value was already found, so that we know that's equal to 1. So 1 is equal to, and I'm just taking the original function, which is x minus 3 squared, and replacing it with c. So 1 equals c minus 3 squared. Right, so to solve an equation like this, you have to use the square root method. So take the square root of both sides. And when you take the square root of 1, that's plus or minus 1. When you take the square root of c minus 3 squared, that's just c minus 3. Add 3 to both sides and you get two possible answers here. You get 3 plus 1 and 3 minus 1. Well, 3 plus 1 and 3 minus 1 work out to be 2 and 4. And remember, your original integral was 2 to 5. So 2 and 4 fall within that interval. So you have two solutions here for C. All right, so now let's look at part C. We're going to sketch the area indicated by the integral from negative 2 to 5 of x minus 3 squared dx, and the rectangle that represents the same area found in part B. And they should be the same. All right, so here's our graph for x minus 3 squared. That's a parabola with a vertex at 3, 0. And I shaded the area from 2 to 5. And then when you compute that area just by doing the antiderivative and plugging in your limits, you get that the area under the curve has a value of 3 units. Similarly, you want to show the interval from 2 to 5. And remember, f of c is equal to 1. So if you were to plug in 4 or 2 into the original function, you get that f of 4 or f of 2 both equal 1. So that's the height or the function value, right? This is f of f of 2 or f of 4 both equal 1. So that's the height. So I showed that work here. And so the area is 5 minus 2, that's the width, times the height, which is 1, which also gives you an area of 3. So they are the same. All right, so that's it for average value and the mean value theorem for integrals. So now you're ready to try the homework. Good luck.